All right, kinematics is basically the study of how position, velocity, and acceleration go together. So we're going to start with just one-dimensional, just a straight line kinematics, okay? And we're going to define, first we're going to define the position, which is essentially just the location of a particle relative to some origin. So if particle is located here at some distance s away from the origin, that's how we define position. Displacement is that change in position. So if I move to a new position, say s prime, that change in position is delta s, which is just going to be, moving from s to s prime. So that difference is just s prime minus s. That's what we call our displacement. Velocity is that displacement during a time interval. So again, I move that position, that displacement, delta s, divide that by the change in time during that displacement, delta t. So we would call that average because that's a discrete set of times. Okay, so some discrete position divided by some discrete time, we call that average velocity. Now, if we want to find the instantaneous velocity, basically we shrink that delta t down to an infinitesimally small dt, and we get the differential equation that velocity is the time derivative of position, ds dt. So that's the instantaneous velocity. That's the relationship between position and velocity. Okay, moving on, we get the acceleration, which is the change in velocity during some time interval. So again, I've got one velocity at the first position, a different velocity at the second position. That change in velocity is, again, delta v, so it would be like v prime minus v, just like s prime minus s was delta s, divided by its delta t. Again, this would be the average acceleration over that time interval that we're looking at. Now, if I shrink that time interval down to essentially 0, I get the instantaneous acceleration, which again is the time derivative of velocity dv dt. Keep in mind, okay, that is also two derivatives of the position. So acceleration is the second time derivative of position as shown here. But again, we usually use the acceleration as dv dt because I don't want to do a double integral. Okay. Now, so these are our two basic kinematic equations. Okay. However, a lot of times it's useful to get rid of time altogether. So here's what I'm going to do. I'm going to take the first equation, v equals ds dt, and I'm going to solve it for dt. Okay, so I bring dt to this side, bring v down to the other side. I'm going to take this dt and I'm going to plug it into my acceleration equation shown here. So again, rather than a equals dv dt, it's going to be dv divided by ds over v, just like I have here. Now I can rearrange this equation a little bit, bring ds to this side, bring v up to the top, and I get the following equation, ADS equals VdV. And again, this is a kinematic equation that does not have time in it, which can be very useful for us. Now, keep in mind, this is not a new equation. It's just a combination of these other equations. So really, I've only got two kinematic equations, but I write it in three different forms depending on the type of problem that I'm trying to solve. Now, these are the three equations that are going to govern all of our kinematic study moving forward. So remember them moving forward.